Hello everybody, welcome to Unit 11. What we're going to learn about is galvanic cells, essentially batteries. So what I want us to understand is how these batteries or these galvanic or voltaic cells work and how these electrons move from place to place in these cells, creating electricity. We've already learned about balancing redox reactions and understand what a redox reaction is with that transfer of electrons. Today that we're going to apply that to galvanic cells to understand them a little bit more. So what this unit is on is it's on electrochemistry. We're studying the electricity produced from chemical reactions that take place. Okay, so in these processes, we see electrons being transferred through a redox reaction. What we can do is we can harvest that transfer electron to get energy to do things like, run our computer, or easy things like light up a light bulb. Okay, we're going to look at how that's being done in these redox reactions. Okay, so just a refresher course on what is a redox reaction. Remember, redox, I had you remember oil rig. You have oxidation and reduction. Okay, so oxidation, losing of electrons. Reduction is the gaining of electrons. Now, this happens together. So if I drop a piece of aluminum, and we saw this earlier this year, into a solution of copper chloride, that aluminum is going to donate electrons to copper. And in that process, copper is going to become a neutral solid and leave the solution and start to precipitate on the bottom, where aluminum chloride is now going to be an ion floating around in the solution. Now, if we do this together, if we just drop a piece of aluminum into copper chloride solution, that transfer happens where electrons are being transferred, but we're not getting anything from it. Now, if we have that take place in two separate areas and connect it with a wire, we can harvest that transfer of electrons and use that electricity to power things. Okay, so if I were to look at this redox reaction as half reactions, remember the first thing I did is I assigned oxidation numbers to each of my elements, with copper being +2, chlorine -1, and aluminum 0 on the reactant side. And on the product side, aluminum is +3, chlorine is still -1, and copper is 0. So notice how aluminum went from 0 to +3. Now, in gaining a charge, becoming more positive, it lost electrons. Okay, where copper gained those electrons and was reduced. So we have our oxidation and reduction taking place, where copper is reduced and aluminum is oxidized. Now again, what we're going to do here is we're going to break this up into two separate parts and have it take place in two separate cells and connect them with a wire and look at how that creates electricity. Okay, but this is kind of just a refresher on how I balanced these redox reactions. So what we're looking at today is how that movement can do things like light a light bulb. And that's what's happening in this batteries. We have two cells where electrons are being transferred from the negative end over to the positive end. And in that process, we have that movement of electrons creating electricity. Okay, so remember, balancing redox reactions, we used the half reaction method to balance them. Where here we have a redox reaction, I broke it up into the reduced portion, into the oxidized portion, and then I equalized that electron transfer. And remember, sometimes it took place in an acidic solution or a basic solution, and that differentiated how I balanced this redox reaction. That changed the method that I used. And remember, we were adding things like water to one end, hydrogen to another, adding electrons, and overall we were coming up with a balanced redox reaction. Okay, so hopefully that's something you remember. That is the first couple questions on the worksheet. Remember, the worksheet isn't mandatory. If you want to skip those questions because you know how to do it, that's fine. Or if you want to go back and practice those, they're there for you. Okay, so that's what we've done already with redox reactions. Today we're going to use them a little bit more and apply them to cells. Okay, so electricity always flows from the place that's being oxidized or losing electrons to the place that's being reduced, which is gaining electrons. So one area is losing electrons, one area is gaining electrons. Okay? Now the area that is losing electrons, remember that's being oxidized. Okay, and the place that is being oxidized, you can also call that the reducing agent because it's supplying those electrons that are being given to the oxidizing agent or the substance that's being reduced, that's gaining electrons. So when I'm talking about agents, it's opposite. These are the things that are supplying the electrons and gaining the electrons. So if a substance is if a substance is losing electrons, it's being oxidized. That substance that's being oxidized is the reducing agent because it's allowing the other substance to be reduced. And that substance that is being reduced, which is gaining electrons, is the oxidizing agent because it's allowing that other substance to be oxidized. Okay, so if I'm talking about the agents, I'm talking about the opposite. Not really important. If we just remember oil rig, okay, the substance is being oxidized is losing electrons, the substance is being reduced is gaining electrons. That's the important idea here. Okay, so in the above example, the electron transfer was direct. Okay, I dropped the aluminum foil into the copper chloride solution, the electron transfer happened, but I wasn't able to harness that energy. This doesn't allow for any useful work to be done by those electrons being transferred. If I have this happen in an indirect means, by having them take place in two separate cells and connecting them with a wire like we saw in our first video, we can harness that energy. And that's where we're creating these voltaic, galvanic, whatever you want to call them, electrochemical cells. Where we have a device where I have two cells separated by a wire where the electrons are transferred, and that wire allows for those electrons to move. And this can be used to do work, and this is what happens in a battery. Okay? So these produce electricity through a redox reaction where electrons flow from one area to another. Okay? From the anode to the cathode, because the anode is where oxidation takes place and the cathode is where reduction takes place. Okay? Now there's an easy way to remember this, just like oil rig is used to remember oxidation is losing, okay, and reduction is gaining. Anox is used to remember anode is where oxidation takes place. This is where the losing of reactions happens. Also, red cat is used to remember at the cathode, reduction takes place, or gaining of electrons takes place. So one thing you would have to do in these problems is identify what is the anode and what is the cathode. Okay, so we're going to look at a voltaic cell involving zinc and copper. Okay, so to create this cell, I have two beakers. And in those two beakers, on the left, I put a piece of zinc. And on the right, I put a piece of copper, and I connect them with a wire. Now, to allow for that loss of electrons, I need to have them placed into a solution where one substance can be gaining those electrons from, and another substance can be adding those positive ions that are created from the loss of the electrons. So these solutions need to take place, or need to be there for the charge overall to be neutral and to supply some of those electrons. Okay? All right. So in these galvanic cells, here we have zinc and copper that we're going to look at. Okay, so the two pieces of metal in the beaker form what are called electrodes. These are the solid portions of the cell that conducts the electrons involved in the redox reactions. Okay, so the solutions are called the electrode compartments, and that is the area where the electrodes are floating in. Now to visualize that better, let's watch a quick video showing this transfer of electrons. Okay.
Useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. and the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and
This keeps the solutions neutral.
maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay, so what we're looking at here is that transfer of electrons, but harnessing that energy by building a cell. Okay, so the same thing that's happening in a normal redox reaction is happening here. It's just that we're separating them and connecting it with a copper wire to harness work that can be done by that movement of electrons. Okay? But if they're only connected by a wire, nothing happens. Because I don't want these solutions to build up a positive and negative charge, I need to have a salt bridge that contains ions that can keep these solutions neutral. So when I'm losing positive ions or gaining positive ions, I have negative ions or positive ions neutralizing those solutions so that I don't have this buildup of excess charge. And we'll look at that in more detail as we go on. Okay, so the anions in the bridge migrate towards the zinc metal because more positive ions are being produced here. So that zinc is dissolving and releasing electrons. So here I would have a buildup of positive charge. So I need the negative ions to move in this direction in the salt bridge to keep this solution neutral. Now, because the copper is collecting those electrons from zinc over here, this solution is losing the positive ions in it. So to replace those positive ions being lost, the positive ions in the salt bridge, and the salt bridge can contain anything, but typically it's going to contain soluble salts because I don't want precipitates being formed here. I want just ions replacing the charges that are being lost or gained. Okay, so here I have a good demonstration showing. Okay, so here iron is my anode, losing electrons. Okay, those electrons travel over here to copper, which is my cathode, gaining electrons. Okay, now to keep this solution neutral, it's becoming more positive here, so the nitrate's going to flow in this direction to neutralize those excess positive ions being created, and potassium is going to flow in this direction to neutralize those positive ions being lost. Okay, and notice what happens to the anode. The electrode gets smaller, and the cathode, the electrode gets bigger. And this continues until I'm out. And what happens to batteries eventually? They die. I can recharge them, so I can force this reaction to take place in reverse by supplying power to it, and that's electrolysis. We can study that a bit later, but this is what takes place in a battery until it's dead. Okay, when is it dead? When the anode has been completely depleted, or the solution of the cathode is out of positive ions, okay, to collect those electrons. Okay, so this completes the circuit, and I have an overall redox reaction. Now, what I wanted to do today is measure that voltage and how it differentiates if I use different cathodes and anodes. Okay, so remember, the mass of the anode goes down, the mass of the cathode goes up because I'm gaining electrons. Okay, now, who is gaining and who is losing electrons? Now, how do I know which one is doing what? Well, I use a reduction table, and this is a table you can find in a textbook or you can print it off. I have given you a link to the reduction table you would have been supplied for the AP chemistry test to use to calculate the voltage of different cells. Now, in this table, this is what it looks like. It's called a reduction table. Everything is measured against a standard, and that standard is hydrogen. Okay? And notice these are all reduction reactions. So these are all show the reactions if electrons are being gained. Now, if I take fluorine here, okay, if I have two cells, one with fluorine and one with hydrogen, fluorine would be the one most likely to gain the electrons. The substance that is towards the bottom is the better oxidizer, or the substance that is most likely to lose electrons. And they're all, again, measured against that standard hydrogen. So this is the voltage created when I measure against the standard hydrogen. Okay? So what I'm going to have to do if I take two of these is, because one is going to have to be an anode and one is going to have to be a cathode, I'm going to have to flip one. Well, which one is most likely to be flipped? The one towards the bottom. Because this one is more likely to lose electrons than gain electrons, because it's going to produce less voltage. Okay, so you could say it's better at giving electrons up than gaining electrons itself. Okay, and what we've been looking at is copper and zinc. And what we said was the copper is better at gaining electrons. Zinc would be better at losing electrons. So when I look at that overall reaction, I flip this reaction because zinc is the substance that is losing the electrons. Copper is the substance that is gaining electrons. And overall, they create that redox reaction, which produces the total voltage that I can either measure with a voltmeter or I can calculate it here. Okay? Now, when this is your table. When you calculate it, you are simply adding these up. If you're multiplying a reaction by 2 or 3 or 4 or whatever, that does nothing to the voltage. What you do need to take into account, however, is if you flip it, you also flip the voltage. Okay? So what we're going to go over is a few examples on calculating voltage of cells. Okay? So the greater the voltage, the greater the flow of electrical current, and you can see these different voltages when you buy different voltages of batteries, a 9-volt battery versus a 1.5-volt battery. Okay? So different substances create different voltages, which produce different amount of power. Okay? So what I want us to do is learn how to calculate voltage. Okay, so the easiest way that I recommend is look up your half reaction. The one that's on the bottom, towards the bottom in our reduction table, is the reaction that would be flipped. I flip that sign of the cell voltage and then simply add the voltage up. Remembering, I don't multiply it by 2 or 3 if I need to add coefficients. Okay, so here's our example, zinc and copper. Notice copper is higher than zinc, so I flipped zinc's reaction. Therefore, I also flip the voltage of this reaction, because this is the amount of voltage produced if I gained electrons, or the amount of voltage required, I could say. If I flip it, this would be the amount of voltage produced. Then I can simply add them together. Now, I could also look at it like this, taking cathode minus anode, but in reality, I like to just flip the sign of the substance that is being oxidized, okay, and simply add up the voltages, okay, and that's how I get that 1.1. All right, flip who is ever lower on the chart, and add them up. Okay? You would always flip the anode here. All right? So we're going to do a few of these, and this is essentially the first portion of redox reactions, is determining voltage. Okay, so potentials again are always measured against that hydrogen ion, which is arbitrarily assigned a voltage of 0. So all of these voltages are measured in reference to hydrogen. Okay, so here let's look at a set of questions that you would typically be given describing a voltaic cell. All right, so here it looks like I have aluminum and lead. Now to create this cell, I have a piece of aluminum floating in a solution of aluminum nitrate, a soluble solvent, okay, or soluble solution of aluminum, and lead floating in lead nitrate, a soluble solution of lead. In the salt bridge, I have a soluble substance. Typically, I like to use potassium nitrate. Okay? So what I want you to do in these problems is label the anode, the cathode, and describe where those electrons are flowing. So who is more easily oxidized, aluminum or lead? If I look at my reduction table, I would look at who's ever lower is most likely to be oxidized because it's a reduction table. The higher it is, the more likely it is to be reduced. So it looks like aluminum is lower, therefore it is more easily oxidized. What is the balanced equation showing the spontaneous reaction that occurs? So with aluminum and lead, it looks like to equalize these electrons, I need to multiply lead's reaction by 3 and aluminum's reaction by 2, also flipping aluminum. So when I flip aluminum and multiply it by 2 and multiply lead by 3, I end up getting this overall redox reaction. The maximum voltage that this cell could produce, well, I flipped aluminum. Again, I don't multiply them by anything, and then I add them together. So I flip 1.66, add it to negative 0.13, and I get positive 1.53. If I get a positive voltage, that is a spontaneous reaction. That would occur and that could produce energy that I could harness to do work, like light up a light bulb or start a car. Okay? So what is the direction of electron flow in this wire? Well, it looks like aluminum, again, is going to be the one that is losing the electrons, okay? So those electrons would be leaving aluminum and moving in that direction, okay? So what direction would the flow of electrons go? From aluminum over to lead, where a lead would be slowly decomposing, okay? Aluminum would be slowly decomposing that electrode, and the lead electrode would be getting larger in size. Okay, what is the direction of positive ion flow in the salt bridge? So, positive ions are increasing over here at the anode where oxidation is occurred. And the positive ions are decreasing over here at the cathode where reduction is occurring. So the lead ions would need to be replenished here. So the positive flow of ions would always be going towards the cathode, okay, where reduction occurs. All right, so left to right. Which electrode is decreasing in size? That is always going to be the anode, aluminum, who's ever losing electrons. Which electrode is increasing in size? Lead. Okay? And if you understand this, this is really the basics of a cell. And that is the majority of this unit. Okay? Is you'd be answering different questions dealing with a cell. A few more dealing with this cell. What is happening to the concentration of aluminum ions? Now, again, remember, aluminum is dissolving, so that concentration is increasing. What about the concentration of lead? That is grabbing those electrons, so that concentration is decreasing. What is the voltage in this cell when the reaction reaches equilibrium? 0. When it's reached equilibrium, it's going to stop. Okay, all the aluminum has been depleted. It's reached a perfect equilibrium. That is essentially when it quits happening. The spontaneity ends. Okay, which is the anode? Aluminum. Which is the cathode? Lead. The positive electrode? Lead. The negative electrode? Aluminum. So the positive electrode is also called the cathode. The negative electrode is also called the anode. Okay? All right, let's do a problem from worksheet 11.1. Now this would be a typical problem you would see on an AP exam. An electrochemical cell is constructed using electrodes based on the following half reactions. Which is the anode and which is the cathode? Well, I would look on my reduction potential table, and here's what I found. I found lead and I found gold. It looks like gold has a higher reduction potential. So who's ever lower, which would be lead here, would be the one that I would flip. Okay? Remember, who's ever flipped is the substance who is oxidized. Well, who is oxidized is the anode. Okay? So, the anode here is lead. The cathode is gold. What is the standard cell potential? I flipped lead, so then I flip that negative 0.13, add them together, and get a total of 1.63. That is my cell potential, or my voltage. Okay? All right. So hopefully that gives you a basic introduction into doing worksheet 11.1. Remember, do what you can. If you have any questions, please let me know. But hopefully this gives you a great introduction into electrochemical cells. See you soon.